Yeah, so I will give you a short introduction into what metamaterials are, and will show you some results we are currently working on, which are able to be reconfigured on the fly. When I did my habilitation, I had to present a topic which was completely not related to MR. And back then, I came across a topic which was quite hot back then. That was about cloaking devices. And those cloaking devices were built with metamaterials. And there was a publication where they showed a cloaking device for microwaves. And that was actually the topic I chose for my habilitation presentation I had to give. And then at some point I realized, oh, wait, maybe those metamaterials are not too bad for use in MRI. So we started to think about it maybe 10 years ago, but as it often is, we did not start working on this before, I don't know, 2016 or 2017. So there's other work on metamaterials in MRI, and I will only scratch a little bit on them and mention them, but it's not a complete overview on metamaterials in MRI. So if I'm missing any work on metamaterials, feel free to add it afterwards in the discussion. So as I said, I don't want to give an overall overview. I really only picked a few other examples, and it's mainly about our work we did recently. And we means being part of the Fraunhofer Society enables us to also get funded projects together with other Fraunhofer institutes. And one of them, the Fraunhofer FHR, has a lot of experience in using metamaterials for the for radar and gigahertz frequency space for antenna design. And we just started a project together with them, and they brought in their experience on metamaterials. We brought in our experience in magnetic resonance imaging, and we fused them. For them, it was really getting to almost static frequencies, going to a 3 Tesla system. And for us, it was really getting to know the world of metamaterials. So let me just give you a rough overview of what I want to talk about. So I first want to give you a short introduction what metamaterials are and what they can be used for. And I know that you all know MRI. Nonetheless, I want to very quickly go over the few different components in MRI which are necessary for imaging purposes, which can be modified with metamaterials. And I will talk a little bit what properties are relevant when we are talking about metamaterials in magnetic resonance imaging. There are different groups of metamaterials. I will try to give a short definition round of how I use the different terms and how I think that those terms are useful. It's not the general understanding of those terms, or might not be the general understanding of those terms, but at least that's the definition I will be using those terms throughout the presentation. And then I will quickly go over different existing concepts on metamaterials in MRI, show you some of the features, why metamaterials are good, for MRI and how they can be used to enhance signal, for example, by a factor of 20 or so, locally enhancing. And then I will introduce metamaterials which can be changed over time, even after fabrication, and that's what's called reconfigurable metamaterials, and how those can be used in MRI. And we are convinced that that's the only way to make metamaterials really useful for applications. And I want to end by just giving you some ideas we have. We haven't realized everything yet we can think of, but nonetheless, I want to share some of the ideas. What is feasible, what could be done with metamaterials. Yeah, when we are talking about metamaterials, we are talking about materials which are pretty similar to typical matter we see, or all the materials we see around. As you know, a typical material will consist of some atoms, and those atoms are maybe elementary particles, and those atoms, they will just come together to build molecules, and then you have your material, you have your matter, which has some dedicated electromagnetic properties and behavior, depending on how the internal structure of the molecules or the atoms are. And metamaterials are pretty much the same, but offer us much more degrees of freedom to actually modify the behavior of a material in terms of how it reacts to an electromagnetic wave or electromagnetic radiation. And we are using, if we are looking at different molecules or atoms, we are using so-called meta-atoms, which are resonance structures. In the simplest case, we will just have a resonant circuit with some inductance and some capacitance. And so the inductance and capacitance are essentially our elementary particles, which we are using to form those structures. And by getting resonance structures, we can modify the behavior because we are in this resonant case, depending on where we are in this resonance, we are getting different effects, different behavior. If our structures are small enough, smaller than the wavelength of our material, the wave won't recognize the atomic structure or the substructure of our material, but rather recognize an material which has some overall properties, like a certain permittivity and certain permeability, and we can modify and construct it exactly in the way we need it. And since we are talking about magnetic resonance imaging, where we have a wavelength on the order of a meter or slightly below in the human body, our structures do not have to be too small to not be recognized as individual structures by our radio waves. And there are some early work on doing this in magnetic resonance imaging. And typically they constructed different structures, which are called Swiss rolls or split ring technologies, which have a size of 1 to 5 centimeters. And in the early work, they showed that you can use this to locally enhance your magnetic field and get a higher signal-to-noise ratio on both the transmit and the receive radio field, which means that you can get signal at least in certain regions, which is 10, 20 times higher than what you're used to by your conventional setup. And almost all of the work showed this enhancement only in for the body transmit coil. For smaller coils, it's a little bit more tricky, and I will come back to this later, how to really achieve an improvement in that regime. We do have some preliminary work where we can show that we might be better than local receive coils. Not by a factor of 20, but maybe by a factor of 2 or so, going beyond what you can reach with local receive coils. As I said, you all know what MRR or MRI is about, how magnetic resonance imaging works. You know, when I put a body into the magnetic field, there will be our macroscopic magnetization, which is forming. And then we can communicate with this macroscopic magnetization by transmitting a radio frequency field, which is on the order of 42 megahertz per Tesla. We are mainly working on a 3 Tesla system, which we have at our institute. There, the frequency is 123. So as you know, it's a Siemens 3T scanner. So it has 2.9 Tesla field strength. That's why it is 123 megahertz instead of 128 or so, what in real 3 Tesla would be anyhow. With this radio frequency, we can stimulate our magnetization to get an synchronized dance or something stimulated, and we will get an echo signal out, which we can receive by dedicated receive coils. It has the same frequency, and we will get exactly this signal back. That will be much lower than the signal we are using for the transmit part, and that becomes important for our metamaterial as well. Come back to this in a few minutes. For spatial resolution, we are utilizing so-called gradient magnetic fields, which allow us to modulate our signal spatially, and in a way that we can get different sinusoidal patterns. And as you all know, that's something we put into our K-space. So we are acquiring the data in K-space regime, and by just combining the different patterns, we get our image out by doing a Fourier transform. So that's just the typical way. We are, for metamaterials, we are dealing with a transmit and with a receive field. And we can modify the transmit RF, the receive RF, and we can get spatial encoding using the spatially encoding metamaterials. And I will also show you a few examples on this later on, so you can get spatial information on this as well. For metamaterials, there are some things to consider. So one is for MR, we are talking about radio frequency. As you know, only the magnetic field is relevant, which is one design feature of a typical metamaterial. Because most metamaterials for other applications, they have to deal with the electromagnetic field, meaning that they have to control the magnetic and the electric field. We are building our metamaterials with mainly the magnetic field in mind and not designing how the electrical field behaves. But that's something I will also come back later and mention again. And something which is important for people working with metamaterials, they are typically used to work in the far field. And as you know, in most applications, at least at 1.5 and 3 Tesla, we are talking about a near field regime, which in principle allows us to being not limited by the wavelength of our radio waves if it comes to imaging purposes. And that's something we make use of by using metamaterials for designing imaging devices without using gradient magnetic fields. Yeah, here just a few of the metamaterials which we build, and I will give you some dive into some of them, not all of them. So those metamaterials are only those we were building in our institute or together with the other Fraunhofer Institute. There are a lot of other realizations, and we are preferring those which we build because they are very easy to manufacture. You can see it's just a PCB board, and you can more or less print just the conducting structures on it. Or ink print it, so it's relatively easy to manufacture and to design them. And yeah, maybe I just move on and give you what I want to show you are three different applications of metamaterials. One pretty short, those are the so-called meta traps, as we call them. Those are more or less a cloaking device, which can hide electric cables in the magnetic field. So the others I will go into a little bit more detail. So the idea is to have a metamaterial which can be clipped around a cable, around an existing cable. So it consists of two different pieces, and you can clip it around the cable. It's very small. It's maybe 1 millimeter thick, and what you essentially do is to create a so-called electromagnetic band gap. There are similar publications or previous publications doing similar stuff with this, which might not be called a metamaterial, but essentially it's it can be called a metamaterial because it consists of the repetition of some microstructure, which is a mushroom-shaped meta atom we're using there for the band gap, and with this you can get at a certain frequency a very high damping, so so that the cable won't show up in the MR, and so nothing goes out, but also there is no coupling into the cable, so you are also preventing any heating issues or disturbance. We used it for an ultrasound, for an MR compatible ultrasound system, where you can just avoid that your RF is actually coupling into the cable. That's just for those metamaterial used for electromagnetic traps. This is not reconfigurable. That's why I'm not talking about it too much, which just leads me to clarifying the different terms. So I will be talking about four different properties or different classes of metamaterials. The first one is just a static metamaterial that's fabricated in one way, and it will never change its property, at least not during the time the metamaterial is inside the magnetic resonance or the MR scanner. So during this measurement process, the material doesn't change its properties, then it's called a static metamaterial. If it is changing its properties over time, it is called dynamic. And if you can adjust it to the resonance frequency of this metamaterial to match whatever frequency you want, for example, your Lama frequency, it would be called tunable. So not all metamaterials are tunable. They are just designed for a fixed frequency. We figured that for any clinical application, I think it will be necessary to have sort of a tunable metamaterial. And it's also tunable not only for the resonance frequency, but also if you want to match impedance, if that is relevant for the application. And when I'm talking about reconfigurable, I mean that we can change the properties during the imaging acquisition in a very dedicated way. So dynamic and reconfigurable means something different, because dynamic and dynamic metamaterial can automatically just behave differently for different scenarios. For example, depending on on your amplitude of the RF field, so that you can separate between the transmit and the receive field. And reconfigurable is something where you can control as an user how the properties look like. So that's a more flexible metamaterial, which can be automatically reconnected or change its resonance frequency on the fly or whatever. And I will show you some examples. And that's what I mean when I'm talking about reconfigurability. So there are tunable metamaterials, and they typically use different approaches. I told you typically you will have a resonant material, so you have a structure where you have some inductive elements, and you do have some capacitive elements. And one metamaterial which is tunable has some wires here which have water tanks here at the side. And by just changing the filling of those water tanks, you can retune your metamaterial to different frequencies. And so you can just by filling in more water or getting out some water, you can change your resonance frequency and tune it exactly to the resonance frequency, to the Lama frequency, for example, if you like. Another approach, and I hope you can see this, is by using some metal stripes in here, which can be moved, and they have this metal stripe which can just be moved over those elements here, changing again the capacitance. And with this, it's a relative elegant way of retuning your metamaterial by just sliding copper strips across your resonance structures. And again, you can just shift your frequency. One problem of those tools is that you have to do it manually, which is not a nice solution for a clinical application or for applications in subjects. And I will show you a way how to do this in a more elegant way. Another metamaterial which is not only tunable but also dynamic is a metamaterial which was presented by a group in Boston from Xinjiang's group. And they are using relatively bulky elements here. They are 3 centimeters high, which has some spiral or coil structures on here, which are tuned to a certain frequency. And by changing capacitance, you can tune it to certain frequencies. And they show that they can use this metamaterial to enhance the signal. So here you have the material with or your phantom without the metamaterial. Here you have it with your metamaterial, and you see that you get an enhancement down here. The same with the onion. It's showing here that you can enhance your signal to noise by just using this structure. But this metamaterial would act on the transmit field as well as on the receive field. And if you want to avoid that it is reacting on the transmit field, because that would harm any human subject you have in there, because by amplifying your transmit field locally by a factor of 20, might just deposit so much energy in this local spot that you might produce heating. So that group came up with a solution which is not really novel. That's a technology which was used, I think, decades ago for automatically detuning RF coils, which is just an additional loop here, which has a varactor diode in here. And this varactor diode will just be conductive for high amplitudes. Otherwise, it would just block the current in here. So essentially, you are having you can use 2 varactor diodes in opposite directions, and they will only actually allow a current in this loop if you have a certain amplitude. If you're beyond a certain amplitude layer, and that's something you what you can use to detune this structure, because as soon as this structure becomes resonant, this additional loop, it will couple with your other resonant structure and it will automatically detune it, but only for the transmit case. And that's working quite well. They show that it detunes for your transmit field. And there are other groups just combine this with the water tanks again for the tuning, and for the then the varactor diodes for the detuning during the transmit field application. It's a little bit bulky because you have to add in this application for each resonator, you are adding those varactor diodes. So that's quite complex and quite complicated. We combined it also with our metamaterial we had before, which was also a stripe element. We are using capacitors which we print into the PCB board, so without having to use additional capacitors in there. And with this, you can clearly see a signal enhancement almost of a factor of 10 with and without this metamaterial. So it's just you're putting this plate in and you're getting this image, you're removing this, you're getting this image. It's just as simple as it is. And it detunes for the transmit case. I already see I have to hurry a little bit if I want to cover everything. We also showed the different effects for the transmit and for the receive part. So we measured the effect for the transmit, we measured the effect for the receive and the combined effect, and just separated both, switching this detuning mode on and off automatically. So in that regard, you can really separate the signal coming from receive enhancement and the transmit enhancement. So we are sure that we are only getting receive enhancement here, and we were able to show that's the image we are getting with a local single loop coil, that's with the body coil. And that's with the metamaterial, so that's without the metamaterial, that's with the metamaterial and the body coil. We could show that we are getting signal improvements which are better than the single loop coil in some areas, but not in all areas. And there is other work which also shows similar effects. In that case, they are showing that the metamaterial can be better, even closer to the coil as compared to an individual coil. But we are not exactly sure where this comes from. We are sort of convinced that our metamaterial is actually amplifying the magnetic field in the outside, in the inside of the structure, and pushing the electrical field outside, which means that the noise, the thermal noise, which is mainly coming from the electrical field, is pushed to the outside. And that might improve the signal to noise even beyond what you experience with a local receive coil. But that's something we have to look into a little bit more detail. What you could see before, maybe just with one coil, you're getting this exponential decay. But if you're combining two of those elements, they will, of course, couple. It's a coupled system. You're getting two resonance frequencies going to the lower one and tune your metamaterial to the lower ones. You are getting a field enhancement which is not showing this exponential behavior of one plate, but just combining the field amplification of both boards and getting a rather homogeneous enhancement in this central part here. And we've proven this with a very professional setup, experimental setup, as you can see here. So again, taking an onion with some shashlik spikes and just having this onion levitating in here, which allowed us to very easily just remove the metamaterial on top anyway, but also on the bottom here, just have it in, have it out. And this is the image what you can get with your body coil without the metamaterial. By just playing a little bit with the level window and level, you see that there is something, but there is just noise. But simply putting your metamaterials in, this is the image you're getting from there. Which is quite nice, quite neat, and shows that that could be a way to get a rather homogeneous amplification over a larger range, even in systems which might couple. And we are getting similar results also in the head coil. With individual coils, it's a little bit more tricky with how they couple to the metamaterials. What we are doing right now is that we are building, as I said, reconfigurable metamaterials. Reconfigurable means that we are bringing active components in. In the simplest case, it's just a digital capacitor up here, which allows us to tune the overall structure to a certain resonance frequency. So even with load, we can retune the system inside the scanner by just using a microcontroller, which we can control via Bluetooth, and then using this digital capacitor. We even extended this, having the microcontroller to control not only one digital capacitor, but controlling 16 different, oh no, 14 different capacitors, so that we can control the resonance frequencies of individual stripes here individually. Again, we have this varactor diode in there so that we are only running this in receive mode. But we can also make this switchable so that you can switch it on for the transmit part. But currently, we are only using it for safety reasons, only for the receive part. And by being able to control those different stripes individually, we can make this structure resonate in different modes. And in this case, so we do have 14 elements. So in principle, we can get 18 and 13 different modes. Here, just 3 different modes where we are using it. It's working oriented in this direction, but you can also reorient it and getting similar results. You can even use 2 metamaterials which are just perpendicular to each other to get resonances in different modes. Which do have a spatial distribution and give you some spatial information on this. And here just also 2 other images. Here is just without the metamaterial, very low noise, and then that's what you're getting with the metamaterial, pretty close to the metamaterial though. With 2 different modes, and by just playing with a level window and level, you are getting a clear picture of the different modes. And if you look closely, you can even see the individual elements of each of those coils here getting depicted in the phantom. And by being able to have more of those elements in place, you are able to actually get an individual stripe image, for example. So you can get resonances where you only have those stripes. You can just reorient it in the way and combine it however you like. For example, you can use it to homogenize your RF transmit and or receive field for this. We do have a mathematical description for this, which works so okay. So on paper, it works quite okay. But of course, if you have different load, it will be pretty difficult to control all the different capacitors. And so we came up with a deep learning based solution, which allows us a neural network to learn the dependencies on how the different patterns look like if you do have different loads in a subject. So you learn. So you can provide a certain profile you want to apply, and then the deep learning network learns how to control the metamaterial to exactly get the same profile you want to get, and these are just the results. Don't want to go too much into details. And then once you are able to get all those different profiles, you can use this to control your receive sensitivity. So you are getting different patterns which you can use for imaging purposes. Of course, that means that you have to control your metamaterial somehow. It takes us approximately 5 microseconds to switch to a different mode. And that has to be synchronized with the MR sequence, of course. And we are utilizing a framework which we built recently, the GammaStar framework, which is a hardware-independent sequence development framework, which we are using to program sequences. And that one is just extended to allow us to also synchronize external signal sources with it. So we do have a driver, and sorry for going over it so quickly. We do have a driver concept which covers the hardware component to control the MR scanner. And this is just able to deal with a stream of hardware events our GammaStar backend is providing and playing it out on the MR scanner. And this GammaStar backend can be extended easily with additional time tracks, which allow us to control metamaterials as well via Bluetooth. So we are synchronizing the MR part with our metamaterial using the GammaStar framework. And the neat thing is that the GammaStar is hardware independent, so this metamaterial could be used in any other MR scanner as well, hopefully. We haven't tested it yet, but that's the hope in the long run. And with that, we might be able to apply different patterns to really do imaging with reconfigurable metamaterials without using any gradients for the imaging part, switching it from pattern to pattern within several microseconds. So that's one project we are working on right now. We are not there yet, but hopefully we will be getting to our next metamaterial, which has much more individual elements than just 14. But I'm quite confident that we will get it at least next year running. Yeah, and then I'm already at the end. I showed you some applications where metamaterials can be used for. So you can use it for SNR enhancement. You can control your electromagnetic wave in the transmit case, in the receive case. So you can start forming or focusing on certain regions. You can build something which is similar to a very flexible virtual coil setup, which allows you to, with an individual coil or coil array, to modify the coil sensitivities in different ways. Could be either used for homogenization or for applying some spatial patterns. And for the transmit case, it could be used to spare out some individual regions. For example, if you want to avoid to apply RF power to a cardiac pacemaker, for example, that could be just spared out by a reconfigurable metamaterial. Anyhow, sorry for being so long. I hope we still have some time for discussions.
Oh, no. Thank you. Thank you so much, Matthias. On behalf of everyone else here, I'm knocking on wood and clapping my hands. That was fantastic. And you could talk on for an hour. I'm very excited.
Definitely.
You made me just realize that I was working on metamaterials too. I made these, we built these dental coils that are passively decoupled in the transmit case, right? You put them on one tooth, and the transmit case, the cross diodes are shortened, and it's non-visible. The atom has vanished, the metamaterial, right? And then in the receive case, the diodes are functional again, and it works. So maybe a provocative question. Can do not the provocative question yet, but how does it what else can metamaterials do except tuning and detuning?
Yeah, it depends on what you're looking at. So, of course, detuning is one part. If you're using an digital capacitor, you can gradually detune, and you can really play with the different resonances, and depending on where you are within your resonance, you can either amplify or you can attenuate your signal. So you essentially, if you want to put it like this, you can. Metamaterial is just a tool to very flexibly play with tuning and detuning of resonance structures. Yeah.
But you can do it on the time scale of the sequence, basically, right? Which is
Exactly.
a new degree of freedom.
Exactly. So it just adds a lot of or a new dimension in this, or even more dimensions, by being able to switching this behavior while you are reading out your signal.
Yeah. And there's a question from Robert from the chat. Are the digital tunable capacitors magnetic? Where to get those non-magnetic digital capacitors?
Yeah, so actually, so those are not magnetic, and they are designed for MR applications. I think they might be using it in RF coils already. At least we just shopped around, and if you're interested in, so I do not have the exact. Maybe I do have.
Maybe it's in the papers.
So in the paper, it's in there, and I might let me see.
So while you look that up, of course, the
Yeah,
audience, I invite the audience to ask further questions.
sure.
If you don't mind to put them in the chat. I have plenty other questions, but
Yeah, no, I don't have it here, but we can send it around.
yeah. You've shown this setup. You've shown your setup where you test your metamaterial and compared it to a surface coil, like a single loop coil or something.
Yeah.
So I have two questions. A, it's basically an inductively coupled coil, right?
Yeah.
So how does it compare? How does it compare to a when we're building these wireless, we call them wireless coils, and we're building them, I get the question, so what do you gain by not using a cable? So the same question to you, what do you gain of not using a cable?
Yeah, so first of all, we don't need any receiving part. Yeah, so it's we are more flexible. So we have a degree of freedom of, let's say, 64 different channels or whatever, which we can add on top of the receive channels. And you can easily just extend it to 128 or to 256 without adding additional receive channels. And so I think it's not replacing any receive coil. It's just extending them and extending the capabilities of it without having a very high hardware overhead you might have for your receive part.
Can you independently record these 128 channels?
Yeah, so we are essentially using an SPI interface. Yeah. And so you can control each one independently.
Yeah, but I mean, on the MRI scanner side, can you record your N channels independently, or you just record one channel?
Yeah, we do not have channels in the MR part. What we are doing is that we are modifying each individual channel to, over time. Yeah, so we are getting the different modes by acquiring signal over time.
So you have one receive channel or one ADC, analog to digital converter in the scanner, and you just use it, you multiplex it sort of in a way.
Yeah, or you using the temporal
Yeah.
dimension to get the different encodings.
Yeah, that's better.
Like you do in your with gradients. Yeah, you are also getting the different patterns over time. Yeah, by applying your gradient.
So while the audience is quiet, on the big picture, why do we want to have gradient-free spatial resolution? Okay, we save building gradients, but do you think there's advantages? It can be better?
So first of all, right now gradients, or let's phrase it that way. The imaging speed is limited mainly by switching or being able to switch your gradients quickly enough. And I'm not sure whether you are aware about this really hyper strong gradients David Feinberg was just getting for his 7T system, where Siemens designed an gradient coil, which I don't know, 400 Tesla per meter and millitesla per meter, and what was it? 4 times switching rate. So it's really incredibly fast, and they put in an effort worth 2 million euros to get just the stimulation away from the neck and shoulder region. So they had to invest quite a lot in there. And if you are not limited by switching gradients, but by switching your receive patterns, where the fields are non-existent, more or less, yeah. So they are so small, you can switch them much quicker.
Sure, yes.
And
Yeah, I can see that.
so you can be faster.
But then again, I would think if you switch away your receive channels, you would lose the signal that you're not receiving at the time.
What do you mean by?
If I'm switching away some receive channels or some receive areas, right? I'm neglecting, right now I say only receive from this channel and this channel.
Yes.
Then of course I throw away the signal of the other parts at that time. But you don't have PNS, you don't have any stimulations,
Exactly.
heating, of course, yeah.
And the interesting part, that's something I'm glad that you're touching this, because right now we are only modulating by amplitude. In principle, you can also modulate by phase. So you can also get phase patterns, and then you wouldn't be losing the signal.
Yeah. And then we are again at I'm not even sure what the word for that is, the phase encoding MRI.
Yeah.
Do you have an opinion about this trace approach where they use RF phase imprinting instead of gradients?
Yeah, it's pretty. So I had a look. I haven't tested it on my own yet. Yeah, but in principle, it's a similar idea and a similar approach. It's just the spatial resolution, which I saw, at least in the publications, was not really convincing yet.
Yeah. Yeah. We have another question from Robert. Robert is asking, what kind of spatial resolution do we expect to get from novel encoding methods based on metamaterial encoding? What is the maximum number of matrix size for 2D image?
Yeah, that's a good point. So we are working right now to better understand which patterns are really penetrating deep enough into our object, because it's if you consider a matrix like a structure where you have individual elements. So that would be this one coil, one voxel approach Jürgen Hennig had back then, without the necessity of being able to read out each individual coil. But if you have a high spatial resolution of 1 millimeter, your typical penetration depth won't be much better. So you will be on the order of just 1 millimeter penetration depth, and then you're getting surface image. That's why we are more looking into structures where we are rather creating like an light tower kind of way where you are really shifting your focus continuously and using this information for spatial encoding. Because if you combine this in two different directions, you can get a combination which allows you to get for each individual voxel a very characteristic temporal behavior. And that's something we are looking in right now. And there we expect to get a spatial resolution on the order of a millimeter. I don't think that we will get below.
Thank you. And before we call this meeting at an end, we're trying to as well to understand our audience. So if everyone's still listening to us, I think quite a few people have left already. Just briefly indicate where you're listening from, just your rough country or time zone. That will be very interesting. We're trying to find a good spot for this meeting. Matthias, thank you so much.